Hello everyone. In today's session, we are going to discuss about the control strategies in problem solving. So it is one of the most fundamental topics in AI. So in this session, we are going to explore what makes a search strategy truly effective. So we will discuss about two, strategies, the BFS and DFS, that is breadth first search and depth first search. We will also talk about heuristics and how they help us make smarter decisions during problem solving. So, by the end of this session, you will have a clear understanding of what it means for a control strategy to be good through an example. So, let us get started. So, before we jump into the techniques, let us ask some fundamental questions. Like, what is a good control strategy? So, in AI, when you are trying to solve a problem, two things are important. First one is it must cause motion, means it must move towards the solution. Okay. So, whatever problem you are trying to solve, so we have seen a lot of problems. So, like the problem of going from city A to city Z. So, it should always start from A and progress towards the goal state, that is Z. That is your a good control strategy must cause motion. Okay. And it must be systematic. That is, it must be organized and it must have consistency. Okay. So, when you try to solve a problem, we represent the problem as a search space. What is a search space? It is a collection of states and transitions between them. A control strategy is a method we use to decide which state to explore next. Very important, right? Okay. Imagine you're trying to solve a maze. The control strategy is a set of rules guiding your decision at every step. So whether you have to turn left, what you have to explore next, whether it is going to be deep path, so whether you follow your instincts. So what kind of strategy you're going to use? So we cannot say that all strategies are really good or that will lead you to a solution. Some might be very poor and you might get stuck in a loop, revisiting the same stage again and again. Okay. So always a good strategy will have motion or movement towards a solution and systematic. Now with this, we will discuss about two requirements. Those two requirements only we are going to talk in detail. Okay. The first requirement is the strategy that must cause motion. So you should always be moving closer towards your solution. Now, let us take an example of water jug problem. Suppose, what is a water jug problem? You have a 4-gallon jug of water and a 3-gallon jug. The goal is to exactly fill 2 gallons of water in the 4-gallon jug. If you try and apply the control strategy blindly, okay, applying any applicable rule or the first applicable rule, say always fill the 4-gallon jug, then you get stuck in a loop and you come to the same stage again and again. So there will be no progress. But a good strategy should have progress. So this is a looping problem. So when you have a good control strategy, it will help you to detect and avoid revisiting already explored state. So we have to ensure that every step is a productive one. The second strategy, it should be systematic. So it should try and explore all the states in an organized and consistent manner. Supposing if you're trying to follow a random strategy, so you try and pick a rule at a random every time. Eventually you will find a solution. But how you found a solution? It might be a very long time to achieve the solution. Might be you would have visited the same states multiple times. But the systematic strategy explores the state space in a predictable, non-redundant order. Very important. So this is more efficient and it gives you completeness. Suppose if a solution exists, surely a systematic strategy will find it. So to summarize, a good control strategy must cause motion and it must be systematic. So these are the two requirements today we're going to discuss. Now we will take the example as water jug problem. So what is a water jug problem? We'll see how the systematic strategy works in practice. So we start with the initial state with both jugs empty. So we write 0, 0. So this will be your root node for a search tree. So from the initial state, we apply all applicable rules to generate the next set of states. So they are called as the offspring of the root. These are the children. The generated offsprings are called as the children. So we will continue until a goal state is reached. So as far as the BFS is concerned, generating children level by level, searching level by level is called as the breadth first search. So for this problem, how to generate the next offspring? Okay. So we can fill the 4-gallon jug that will give you a state of 4, 0. Or I can fill a 3-gallon jug that will give a state of 0, 3. So these are the two children's. Okay. So instead of immediately going deep and then trying to find a solution, so what we can do here is the BFS searches level by level. So we'll try to explore all the nodes at the current level before moving to the next level. Okay. So from the top to bottom. So this process will be continued until we reach the goal state. Now, we will look at the first level, how the children are generated. So starting from the root node 0, 0, we initialize that both jugs are empty. This is the first. So how many children can be generated? 2 children can be generated. The first child is 4, 0, that is filling the 4-gallon jug, and 3-gallon jug is empty. Other possibilities, filling the 3-gallon jug, 4-gallon jug is empty. So this is level 1. Okay. So at level 1, we have two nodes, that is 4, 0 and 0, 3. So this is our first layer of our BFS tree. Now before going in deep, before expanding any of these two nodes further, BFS will first explore, make sure all nodes at this particular level are generated. Now we will try and generate the next level from here. So now you can see the two levels. So in this, you can see here, this is level 1 and this is level 2. Now from the level 1, suppose we start from 4, 0, the 4-gallon jug is full and 3-gallon jug is empty. So applying several rules, what are the possible states can be achieved? So you can pour the 4-gallon jug into 3-gallon jug So we fill the 3-gallon jug and we have 1 gallon left in our 4-gallon jug. So this gives a state of 1, 3. This is one of the rule. Second can be simply filling out the 3-gallon jug. So we are here, already 4 gallon is filled. Simply we can fill this 3-gallon jug. Okay, right? So otherwise we can empty the 4-gallon jug. So that will be this state. But if you see, the state is already visited. 0, 0 is already visited. So we have to skip this state. So this is one possibility. Second possibility, if I am here, from 0, 3 means the 3-gallon jug is full. What we can try and do here? We can pour the 3-gallon jug into the 4-gallon jug. So we will get this state 3, 0. Okay. Otherwise, simply we can fill the 4-gallon jug. It will be 4, 3. Otherwise, we can pour this 3-gallon jug into the ground. So we'll get this state. But again, this state is already visited, so we will avoid it. So notice that BFS processes all level 1 nodes before going to the next level. So this is defining the characteristics. It ensures we find the shortest path before we explore all the possibilities at each depth. So BFS guarantees if a solution exists at depth D, we will find it before exploring any states at 3 plus 1. Now, we will see the consolidation. Like we will see the search process, how it happens with BFS, DFS and heuristics. Okay. So, first we'll talk about the BFS. BFS explores all nodes one level before going deeper to the next level or the next step. So it is very systematic and very complete. And if a solution exists, surely BFS will find it out. It guarantees the shortest path to the goal. But what is the main drawback here? Since exploring level by level, all nodes at the current level must be stored, which will be very, very large. That's the only drawback. But if you take the DFS, it's another important strategy like BFS. So instead of exploring wide, we go deep. We pick a path and follow it way downwards until either we find the goal or hit the dead end. If we hit a dead end, what we have to do? We have to backtrack and find a different path. DFS will obviously use less memory than BFS because it needs to store only the current path. However, it might get trapped on a very long infinite path if we are not careful. So, does not guarantee to find the shortest path, but BFS will surely find the shortest path. Okay. For example, imagine that you're searching a tree with a goal at a depth 3. Suppose if you are using a DFS strategy, it explores the branch that goes 10 levels deep before backtracking. It will find the solution, but it's a waste of time going deeper to 10 levels where your solution is at 3. So you will have to store a lot of irrelevant paths. So which is better, DFS or BFS? So it depends on what kind of problem you are dealing with. When you want to find the shortest path, you can go for BFS. When you are wanted to use less memory, better memory, and if you find the solution to be very deeper, then you can go for DFS. Next, we'll talk about the heuristics function. So, as far as BFS and DFS are concerned, both are uninformed, blind searches. They explore without any specific knowledge about where the goal is. But if we could guide the search using some kind of domain knowledge, this is where the heuristics comes into the action. The heuristic function estimates how close a given status to the goal state. So it does not mean that it will not give you an optimal answer, but it guides your search towards your goal. It will give you promising paths. If you have more accurate heuristics, you'll have to do a very less number of searches. If you have a perfect heuristic, sometimes directly you can go to the goal without any explanation. However, what is the trade-off? Computing the heuristics itself is a cost. Okay. If you have a very long, complex heuristics might take a very long to get evaluated. So possibly it will negate the savings from reduced search. So a well-defined heuristics balances accuracy and computation cost. So this is a key insight in AI search where A-star algorithms come in. A-star algorithm is an informed search strategy that use an evaluation function f of n is equal to g of n plus h of n, where the h of n is your heuristics and g of n is your path cost. So to summarize whatever we covered, so we started by talking what a control strategy is and why it is important. So we talked about two important requirements. That first, a good control strategy must cause motion and it must be systematic. What do you mean by causing motion? You should ensure that you are moving towards the goal and you're not stuck in a loop. What is systematic? So ensuring states are explored in organized and non-redundant manner. So we discussed about the water jug problem where we tried and built a BFS tree level by level. Then we discussed about the comparative analysis of BFS, DFS and the heuristics function. So BFS is complete and when you want to find the shortest path, it's very useful, but when it's going to occupy a lot of memory. But when you take DFS, it uses less memory, but it goes very deeper and it does not guarantee to find a shortest path. Finally, we talked about the heuristics, which helps you in a smarter way to achieve the goal. So you cannot say that this is the best strategy. So depending on your problem structure, available memory and whether an optimal solution is required or not, the choice depends on what kind of algorithm you use. So these are the references from Swat Russell, Parag Kulkarni and Elaine Rich. Thank you.